So previously we have been talking about kinematics of particle, basically the study on motion, how to get velocity, acceleration, and displacement when a particle is moving in a straight line or in equivalent motion. We have covered all those. Now we want to see the relationship between force and motion. Okay, the force that is causing the motion. Um, it's not enough to know just the motion. We want to know what would be the force needed to cause this kind of motion. Because in the end, we might be designing certain machine, certain mechanism that move in a certain way, and we want the system or the arm, for example, to move in a certain way. But to move it in that way, we need to know what would be the required force to cause this kind of motion. Okay, this force will be used in terms of auto sizing later on. So in terms of the forces causing the motion, okay, we have three approaches that we will be looking to in this course. The first approaches will be to use our infamous Newton equation F equals to ma, and the first approach using F equals to ma equation. So even the equation itself uh, shows us that we are relating the force with the motion. Okay, the motion comes in the form of acceleration. Okay, so this is how we relate force with motion, or with loading parameters with motion parameters. The next approach is using the work and energy approach. Okay, in the case of work energy approach, instead of relating force with acceleration, now we relate force with velocity. Okay, so we'll have work energy equation, whereby in this equation we'll have force and velocity. Okay, we will not have force and acceleration. And lastly, we'll be looking into impulse and momentum problem as well. Okay, this approaches is used when we are solving for impact problem. Okay, then we will see later on what we meant by impact problem. Okay, so we'll start off with the first one. Okay, the most obvious one, which is using the Newton equation. So we'll be using F equals to ma. Of course, in the real world, we might not have only one m or one force. We need to consider summation of forces acting on that particle, and that will give us work ma. So F equals to ma is a Newton law, the second Newton law. We are relating force with acceleration, okay, through the mass here. And in using F equals to ma, we will be seeing this a lot, which is our gravitational force, or normally termed as our weight, is equals to mg. Okay, and weight will always be acting downward, while our g, which is the gravitational acceleration, will always be taken equals to 9.1. Of course, g depends on location. Okay, in the real world, g might change a little bit here and there, but we'll take this as a constant value equals to 9.1, and it is pointing downward towards the center of gravity, or in this case, center of the earth. We will also be using this a lot. Okay, frictional force. All right. When we have friction, uh, we can look at this equation, friction equation, to guess when friction is important. Okay, so we have two parameters here: the coefficient of friction and the normal force. Okay, normal force exists when we have contact. Okay, or we have two contacting surfaces. If the surfaces are not in contact, we will not have any normal force. Okay, and if there are no normal force, there will be no frictional force as well. Okay, and this guy, this mu, will be our coefficient of friction, and it will depend on surface roughness. Okay, if our surface is rough, we will have mu. If it is smooth, we will not have mu. Right? So frictional force will depend on these two. The direction of frictional force will depend on the motion. Okay, depends on motion, and it's always against the direction of motion. Okay, is the keyword here, against the direction of motion. So if we know that the motion of a particular object is moving to the right, friction will be to the left. Okay, it is against the direction of motion. And of course, if the object is uh, not moving yet, we will have what we call as static friction. And if the object is already moving, we will have kinematic friction. Static friction will always be larger than kinematic friction. Okay, sometimes we give those information in a question. Sometimes we just assume one value of uh, friction coefficient. Okay. Next, we have forces that is being transmitted through cables. So in the case of cable, we will assume that our cable to be having a constant length. Okay, meaning it is not extensible. Okay, so the force within the cable will also be constant. Okay, since the cable cannot be extended. All right, and of course the cable can only be transferred when the cable is in tension. Okay, the force can only be transferred when the cable is in tension. Okay, you cannot transfer the force within the cable when the cable is slacking. So that means you can only pull a cable, you cannot push a cable, right? So that will give us an indication of the direction of force within a cable. It must always be out from a point. And lastly, when we use this Newton equation F equals to ma, we cannot run away from using free body diagram. So free body diagram is a must in this approach, and this will be our starting point to solve the problem. All right, clear? Everyone is clear about this? Okay, just to illustrate the point, let's say we consider this simple example. Right, so we have a mass uh, 5 kilogram on this surface, and it is being pulled by this inclined force, which is at theta from our horizontal axis. So now we need to determine what's the exertion of this block if the coefficient of friction is equals to 0.5 and sine theta is given equals to 0.6. Okay, fine. So the first step is to draw our free body diagram. So we have a 5 kilogram block, okay, and it is resting on the surface. We remove the surface, we will have our normal force. And of course, since we have a mass here, we will have our weight as well. Next, we have the 50 Newton force and angle of theta. Okay, so this is our free body diagram. We free the body from its support and we put all the forces that is being applied to this body. When we remove the support, we have to replace those support or connections with the effect of the supports and connection, in this case in the form of normal force. Right, this is our free body diagram. And of course, normally we will draw another diagram, okay, just to illustrate the motion of the particle, and we call this as our kinematic diagram. Okay, what's in it? What's in this kinematic diagram? So it's just the mass and its acceleration direction. So acceleration in this case is a straight line direction. Okay, A. That's it. Okay. So why we want it to be why we want to have these two diagram, because we know we are using the equation F. This part represent the F within the system, and it is equal to mass times acceleration. Okay, so for the free body diagram, we'll be looking at the summation of forces acting on the system. For the kinematic diagram, we will be looking at the acceleration part or the motion part of the system. Okay, so we'll be using these two figures to aid us in solving the problem. I missed one force here. That force is our friction force actually. Okay, and in this case, if we imagine ourselves pulling in this mass, it is moving to the right, so the direction of motion is to the right. That means our friction force should be to the left, and it is acting at the contacting surfaces between the mass and the surface. So actually we have additional friction force here to the left. All right, so the same goes here. Right. Once we have this, now we want to use our Newton equation. Summation of force equals to ma. For the summation of force part, we'll be referring to free body diagram. For ma part, we'll be looking at kinematic diagram. Okay, the summation of force equals to ma. Of course, this can be resolved along x and y, so we'll have summation of force along x equals to ma x. Summation of force along y will be equals to ma y. Okay, m will always be the same. There is no m along x or y. Okay, but acceleration or the motion can be decomposed along x and y, just like our force vector. So we'll be looking along x-axis first. The summation of force along x, we refer to our free body diagram. In this case, we'll be taking positive to the right. So we have 50 cos theta minus mu n, then equals to summation of force. Okay, this is the summation of force part equals to m is 5 ax. Ax is our e. Okay, that's it. We can't solve the problem yet. Okay, if we look at the problem along y-axis, taking positive upward, so we have summation of force along y equals to ma y. So we have 50 sine theta plus n minus w equals to m 5 ay acceleration along y. In this case, all the acceleration is along x. This guy is ax. Okay, ay is equals to 0, so this part will be equals to 0. So from this, we will have our normal force, which is equals to weight plus 50 sine theta. Normal force is equals to weight minus 50 sine theta. Okay, once we have this, we can substitute this equation number 1 into equation number 1. So we'll have t cos theta. Okay, now we have the option of calculating what's the angle theta, or instead of doing that, just use the information given here. Again, normally I will be using the information given here. So sine theta, so what we have a triangle like this, theta. Sine theta equals to 0.6. So one of the obvious value of sine theta will be coming from 6 over 10. Okay, a triangle like this. Okay, 6 over 10 will give you 0.6, which is equal to sine theta. Okay, so if we have a triangle like this, 6, 10, this guy will be equals to 8. Okay, the base will be equals to 8. So in that sense, we can get cos theta is equals to 8 over 10, or basically equals to 0.8. Right? So straight away we can get cos theta. without knowing what's the actual value of theta. The cos theta here will be equal to 0.8 minus mu. Mu is given 0.5. And is this guy here. Or if I want to expand this guy, it will be equal to 50 times 9.1 minus 50. Sin theta is 0.6. So we have a value for n is equal to 460.5. Okay, Newton. This is our n. So we'll be substituting at n here. We have 460.5 equals to 5 times acceleration. Okay, so acceleration now is equals to 50 times 0.8 minus 0.5 times 0.5 divided by 5. Now I got A equals to minus 190.25. Okay, let's try another example. In this case, we have two mass, A and B. Okay, we were told that MA equals to 2 kg, MB equals to 10 kg. If the coefficient of kinetic friction between block A and the surface equals to 0.2, we need to find the tension in the cable and the acceleration of both blocks AA and AB. Okay, fine. In this case, since we have two masses, that means we will have two free body diagram and two kinematic diagrams. So let us consider free body diagram of A first. So for A, we will have our MA, which is equal to 2 kg, and we'll have our normal force, always 90 degrees with respect to the surface, and we'll have tension coming from the cable. And of course, we have weight always pointing downward, and since in this case A is on this surface and the coefficient of friction given equals to 0.2, based on the mass alone, let's say MA is 2 kg, MB is 10 kg, we are expecting that A is moving upward, right? So if A is moving upward, the direction of friction force should be in opposite direction. And then we have a kinematic diagram of A. Okay, that's it. So we will get the equation for this guy. In this case, since A is on a slanted surface, we'll be using a slanted surface instead, dash y dash. Okay, in this case, so we'll be solving our Newton equation using these two axes. So along this dash, what we will have summation of force along x dash equals to M A x dash. The summation of force along x dash will be equal to E. To be more precise, this positive along this direction. So we have T minus mu N. The angle here will be equals to 40 degrees. Okay, based on the angle of this slanted surface here. This will be equals to 2 times AX, which is our A. Okay. And along Y dash, again to be more precise, this is the positive direction. So what we'll have N minus W cos 40 degrees equals to M is 2 times the acceleration along Y dash is 0 again. So we have N equals to W cos 40 degrees, and substitute the values here. 2 times 9.1 cos 40 degrees. So we have our n. This equals to 15.03 Newton. Okay, I spell it out here so that you'll not be confused with this n. Okay. So once we have our n, we can substitute our n back here to simplify this equation. So mu is 0.2. Okay, this will give us our first equation. We have two unknowns, t and a. So we cannot solve this since we have one equation, two unknowns. Okay, fine. So we need another equation, and that equation will comes from member or block B here. So we'll be repeating the same approach now for B. Reword again for B. B is having a mass of 10 kilogram. And it's input by the cable, so you have tension from the cable. Okay. Bear in mind, we have only one cable here running through this pulley here, so the tension of the cable will be the same anywhere on this pulley. So if we have T for A, the same T will be applied at B. Then we have the weight as a waist pointing downward. That's it. B is not in contact with anything, so there will be no friction. So for the kinematic diagram of B, if we are saying A is moving upward, so B must be moving downward. It doesn't make sense that A moving upward, B is also moving upward. Okay, if A is moving upward, B must be moving downward. So the acceleration at B is downward. And since A and B is connected through the same cable, so the motion of the cable will be the same. So the displacement at any point on top of this cable will be the same. That means velocity at any point on top of this cable will be the same, as well as acceleration on top of this cable will be the same. So if we are looking at this point, if this point is moving with A, anywhere on this cable will be moving with A. The same with this point here. So in that sense, we know that actually AA is equals to AB, which is equals to A. Okay, because they are interconnected through this cable actually. So that's how we know it's A here. Alright. So once we have this, we'll be using summation of force along normal x and y axis in this case. And since the forces are all along y axis, even the motion is also along y axis, we don't need to consider the x axis, okay, because all of them will be equal to 0. Then we'll take summation of force along y equals to m a y. So in this case, we have T minus the weight. And this weight will be different compared to the previous weight. This is weight for B, be more precise. And this is the weight for A actually. Okay, T minus weight equals to M for B. Okay, previously it's not just any M, this is M for A. For A. Times A. Alright. So substitute the values that we know. T minus 10, 9.1 equals to 10 times A. So this will give us T minus 98.1 equals to 10 A. This is our second equation. Right? So in this case, instead of stopping here, I can also rearrange this straight away. T equals to 10A plus 98.1. Okay, this is our second equation. So what we are going to do, we're going to substitute 2 into 1. So the first equation is this equation. So we'll be substituting for t there.
Doctor,
Yep.
why are we using 5 in equation 1? Should be 2, right?
Yeah, you're right. Thank you. We'll have 10a plus 98.1 minus 0.2 times 15.03. For our a now will be equals to, okay, I just rearrange the equation. I'm taking 2a goes to the left hand side, so we have 8a. And so 98.1 go to the right hand side minus 98.1. This part goes to the right hand side, so it becomes negative. This part goes to the right hand side, becomes positive as well. So the sum of these divided by 8 will give us a. So a will be equals to, I got a equals to minus 10.31, which means a is actually moving downward, not upward. Hopefully the calculations are correct. Okay, feel free to verify the numbers here. Okay, so once we have a, so t is just equals to 10 times. Now this is funny. I got t equals to minus 5, which is not logic. Okay, the tension cannot be negative. In this case of cable, it should be always positive. You can always pull a cable, you cannot push a cable. So something is wrong somewhere. So we have t, we have mu n, fn. Oh yeah, okay. Can you see the problem? I've seen the problem already. Okay. The problem lies with my question here. Okay. I forgot to put a minus sign at the acceleration. In this case, B is moving downward. So A here should be negative. Should be negative A. So the sign here should be minus sign. We have minus here, minus here. So here we have minus 10A plus 98.1. Right? So once we have that, so here it should be minus sign there. So once it is a minus sign, so if I bring this over here, so minus minus, it should be minus 12. So the answer here should be 6.7. Okay. So once we have that, so tension will be equal to 166.8. Okay. It's good that I've made some mistake there, so that we can see what happens if we do a mistake. Okay. Always look at your final answer. Okay. Your final answer should be logical. Okay. Dynamics is based on physics. So in this case, if we are saying that we have two masses here, B is heavier than A, so we are expecting that B will pull A upward or B will be moving downward. And when we consider that as our direction of acceleration, we should get A that is positive. If A is negative, then it could be something is wrong somewhere. Furthermore, if we have tension in the cable to be negative, that is completely wrong. Okay, acceleration can be assumed to be upward or downward. Okay, it depends on the value of the masses A and B. However, for tension in the cable, it will always be positive or upward from the point. Okay, so this will always be correct. Okay, so this direction is the actual direction for the force within the cable. All right, there's no other way, no other option. As for the acceleration, okay, of course, we can have the mass moving upward or downward, the incline depends on mass A and B. Okay, however, for the tension within the cable, it is always out from the point. Cable will always be in tension. Okay, so that's how I know if I got T here equals to a negative value, so that the answer will be completely wrong. Okay, we need to stop and trace back what we have did before and try to figure out what went wrong. All right, clear? Any
Excuse me,
question?
doctor. For the value of tension, it's gonna be minus 10 into 6.87.
Oh, we have minus sign here.
Yeah,
That's minus sign plus. So this one should be equals to.
it should be 29.4.
Okay, it should be 29.4. Okay, my bad. You're right.